Right, ready? So we're gonna focus on momentum, right? So as we said, Elena, if you have an object and the object has a mass, if the object moving in one direction, it's moving with a velocity v, then the object has a momentum. The symbol for momentum is mass multiplied by, sorry, the symbol is p and the formula is mass by velocity. What's the SI unit? It's kg ms minus 1. Right? Kg ms minus 1. We need to remember as well that momentum is a vector quantity. So for example, if something going this way, momentum might be positive. If something going the opposite way, momentum will be negative. All right? So just remember that, right? That momentum is a vector quantity. One direction positive, the next negative. All right? Now we're going to focus on something called collisions, right? Conservation of momentum. I don't know. Bye-bye. I don't think so. All right. So let's take a look at something called the conservation of momentum, right? So we learn what is momentum. Momentum is just multiplying an object's mass by velocity. All right. So if I have an object and it's moving, right, that object has momentum. Its momentum is its mass by whatever, however fast it's moving, right? Now there's a next law called conservation of momentum. You ever heard about conservation of energy? Right? Energy can either be created or destroyed, but there's something called conservation of momentum. If you have two objects, right, and those objects moving in opposite directions and they collide, here's what the law says. The law says that if we find the momentum before they collide, it will be equal to the momentum after they collide. So if they're moving like this, they both have momentum. When they collide, this might happen. So if you find the momentum when they're moving like this, and when they're moving like this, both momentum should be equal. And that law, or that conservation, is called the conservation of momentum. That's okay? So what the law says is that if I were to work out the momentum before something collides, and then work out the momentum after it collides, they should be equal. That's okay? They should be equal. So let's work out the momentum here for now. What's the momentum of the object, of this object here? Momentum, huh? Mass by velocity, right? So the mass is 2 and the velocity is 10. What's the momentum here? I'm missing.
No. -2.
-2. Because we said momentum is, right? Because we said momentum is a vector quantity. One direction positive, the next direction is negative. Here, it will be 4 by 2. Right? Oh, wait. Anyway, and here's how much? By +2 because they're in the same direction, right? So let's work out this. This is 20 minus 6, which is 14. kgms minus 1. What about here? 8 plus 6, which is 40. That's okay? So the momentums are equal. Therefore, it means that we know it conserves. Right? So suppose I did not know the speed that the 3 kilogram moving with. How could I work it out? So, right, you find for the velocity here. You work out this, you create an equation and you solve. Right? Why? Because we know that momentum before equal to momentum after. Right? Copy the small calculation down and then I'll give you a note, right? 14 kgms minus. Right, next law. Write this law down. The law of conservation momentum states the law of conservation of momentum states that when two or more bodies collide, the law of conservation of momentum states that when two or more bodies collide, the total momentum before collision is equal the total momentum before collision is equal to the total momentum after collision. Is equal to the total momentum after collision. After collision. Provided that no external forces happen. Provided that no external forces happen. Right? So in short, total momentum before equals the momentum after. Right? So in short, that's what you'll do, right? So what we're going to attempt now is we're going to try to apply that rule to a couple of situations, right? All right, let's try one. Number one. Actually, before we do that, let's show you the simulation here. You've ever heard about the Newton's cradle? No? Alright, so watch this here. This is called the Newton's cradle. Right, online, you're seeing that? Eyeballs, different colors. Online, you're seeing it? Online. Anybody there? Alright, that was there. Right, what do you think gonna happen, Sanjay? When I move the red board, what do you think gonna happen? Yeah, so I pull it away and I release it.
It will stay. No, it will press. No, I think.
All
I think last one.
what you know that's the momentum before equals to momentum after. So when I release this, the momentum before should be equal to momentum after. So make a guess.
Last one.
Last one. Let's see. Right? So the momentum before equals to momentum after. Right? So you see that here, momentum here and momentum here, C. One ball, all identical. What's this long? What happened here?
The last.
That's now. Was it be stationary? How this stuff? Right? They both have the same momentum. Okay? And kind of Newton's third law as well in the middle here. What would happen now if I move 3?
Oh,
I move 3. How much will move on the next side? Yeah.
oh,
So the law has to stay the same. The law has to stay the same. Right? So 3 balls on the left means 3 on the right because they're moving at the same speed. Right? This is a demonstration of Newton's third law and conservation of momentum. That's okay? So this is a perfect example of how it works, right? I started wanting to show you this. It's called Newton's cradle and it explains Newton's law and also conservation of momentum. Well, why not? Let's just forget about the one. Alright, so let's try this one here. Two objects of equal mass, 4 kilograms. Two objects of equal mass, 4 kilograms. Two objects of equal mass, 4 kilograms. Collide head on. Collide head on. With one moving at a speed of 5 meters per second. With one moving at a speed of 5 meters per second. And the next with a speed, and next with a speed of 2 meters per second. And next with a speed of 2 meters per second. First up, if they both move off together with one speed, if they both move off together with one speed, so like they stick up together, right? If they both move off together with one speed, calculate that unknown velocity. Calculate that unknown velocity. Calculate that unknown velocity. Calculate that unknown velocity.
first.
Huh?
First.
Yeah, well, then what would the same velocity here? So technically the velocity. Right, but some people started, so that's good. So what's the momentum here? What's the momentum here, Elena? You just want to come on. What's the momentum here? 4 by 5. 4 by -2. Nice, because it's in the opposite direction. And what's the momentum here? What you could do is treat them as one, right? So you could treat them as one, 4 plus 4 by V. Or separately if you want, 4V plus 4V. Right? No matter. So when you work this out, this is 20 plus -8. That's 12. Right? And here is 4 plus 4 is 8. So you can solve for V. V is 12 over 8 meters per second. Or you could write 1.5 meters per second. That's okay. So it's important that we set up a nice little diagram, work out everything before, everything after, and then solve. That's okay. So 1.5. Well, okay with that? Okay with that? Great. Any questions online? All right, so let's try this one here. Hold on. Wow. Let's see if I get this to work first. See, that is- So in truck of mass heading north, and then you have a car head on. Right? They want you to find the initial, the final, and then the speed of them together after. Okay? You can draw a diagram, that will help you. You don't want to draw a truck, you just have a circle or box or something, right? That's it up. Yeah. Just like how we did this one, can you treat them as one, add them up and move them together. Right, so a truck of mass 1250 heading north. Slammed head on at 25 into a 625 kilogram car. Moving south, get that is opposite direction, right? Assuming that they move up what speed and direction of the wreck right after collision. So you might have something like this, right? But you have to answer it in parts, right? So they want the momentum. They want the momentum before collision. So the momentum before collision, that'll be 25 by 1250 plus 625 by minus 30. How much is that?
131,253.
3, 1.
Yeah.
Yeah, when you add it up and minus it. 12500. Anybody else get that? That's it for this whole thing, right? All together. And then they ask for, did they ask for momentum after?
Momentum before truck only.
Or for the truck only and then for the, okay, I'm now wondering how they want it to. Right. So momentum before for the truck. This was 31250. Part 2, they want the momentum of before of the car, right? So that would be 625 by minus 30. Right? You have to show you the direction from there. How much is that? And now in part 3, they want to work on P, right? So before you start anything, you have to tell them the law. Total momentum before collision is equal to total momentum after collision. Right? Total momentum before collision equal to momentum after. Before collisions, we have to add these two up. So that'll be 31250 plus minus 18750 is equal to momentum after. We know that they stuck up together, so that'll be what? 1875 by V.
Oh, yeah.
When you add these two together. So mass by the velocity. Okay? And then when you work this out, you'll get V to be, what's this minus this? 0 divided by 1875. Right? You okay with that? So you work out the momentum before, and you get 12,500, and then you divide it by the total mass. How much is that?
No.
Right? 6.67.
Yeah.
And then positive, so it will be the north direction. Because I chose positive as north. This is south. Right? So this will be towards the north. That's okay? Any questions online? All right, so this one a little bit different, it's more theory, right? But it's the same question. Hold on, huh? That's not one. right? Take a little read, tell me what you think. Yeah, well, take it now. Yeah, they have taken too long. Right. For the next from. Yeah, you can take too long. So that makes sense. So you got somebody else. But confirm with the next guy, you can comment first, right? Okay, so this question a little bit different, is more theory, right? So you need to have numbers to work with, but you could put in some numbers and explain what happened in there, right? So you have two trucks, they have identical mass. Take a little read, right? You can draw the diagram and some more you think.
Good. Yeah.
Right, Vinaya. So, could you explain what happened there? So, what we have two trucks, equal mass, heading opposite direction. So you can draw it. It's a velocity of V. right, at the same speed on a busy east-west highway. They both remain stationary on impact. Explain in terms of conservation what happened, assume that the masses remains. Why did they remain stationary?
Because momentum is
Yeah,
would be equal to momentum of the second term.
okay.
Yeah, because it's mass speed same.
And
Um,
why they remain stationary? Anybody? Why they remain stationary? Same trucks, both have a mass m, both moving in opposite directions with a velocity v. Yeah. Both momentum, okay. But both forces, all right. Right? If you were to add those two, if you were to add the momentum of the trucks up, one is mv, what's the next one? Minus mv. So when you add mv and minus mv, your total momentum is what? 0. Right? So if the momentum before is 0, it automatically means that the momentum after is what? 0 as well. Okay? And since the masses remain the same, what would I have in 0? Velocity. So that's the reason why they were stationary after. That's okay? So write this down. Write this down. Since both trucks since both trucks had equal momentum, acting in opposite directions, then their total momentum before collisions, then their total momentum before collisions then their total momentum before collisions is equal to 0. It's equal to 0. Full stop. This implies that the momentum after collision. This implies that the momentum after collision This implies that the momentum after collisions is also 0. Therefore, the trucks the trucks would remain stationary after impact. Therefore, the trucks will remain stationary after impact. Next one. A little bit harder than the others, huh? Draw a diagram. Try that. But these are the older years. Normally we practice the older years and lessons, and when it comes to the core exam, that's what the guru said. That's kind of leave out the last 4 or 5 years for core exams. So you have to figure out what's before and what's after. Change of diagram now. Is a bullet, not target, right? So draw the bullet before, target before, and then draw it after. And put in your values. Everything should have a mass, everything should have a velocity. Like we just now, give it some time ago. Right, it completed diagram might look something like that. Right, it completed diagram might look something like that, right? All right, let's see what you got. Finish. Finish. Let me see. All right, and that's split it in the middle, right? So what's the momentum before? Well, you might recognize that we don't know the velocity of the bullet, and the velocity of the target was zero, that is stationary, right? So the total momentum before would have been 0.1 multiplied by v plus 5 multiplied by 0. Momentum after will be 5.1 multiplied by 6. Right? Why I have 5.1? Right, so add the 5 and I add the 0.1. And now just to solve for b. So I got b to be 5.1 multiplied by 6 over 0.1. That's about 306. So the speed of the bullet is 306 meters per second. All right, online? Anybody got that? You got that? Right? 306 meters per second. I think we can squeeze in one more.
Yes.
Right? This one combines everything that we did. If you can't see, it's on page 43 in the handout, right? If you go back to your topic, right? Topic is on page 43. Don't understand why we start there. In fact, you go to page 43. We just going for some good now. Go to the topic by topic, page 43. And do the whole question for now. You go on, forget, you go on, yeah. Huh?
What's yeah, one. Speed walking. Yeah, I know how to. What happened? Right. Really? Eat this one. No. Ano yan? I did. Right. Yeah. You know, the next thing.
Right, you're done the whole thing, right? Hope you'll finish the whole thing, huh? You'll do this part alone? You give all the time to go through all the parts. Oh, you try, okay, yeah, okay. So that was it, a little bit different. Alright, so a crash test, a car traveling at a constant velocity of 26 meters per second. Right, crashes into a wall and is brought to rest. Find the initial momentum We know that momentum is mass by velocity, right? Remember I told you how to answer questions, right? FSE formula,
Statement.
formula, substitution answer, right? Good problem. Right, anything? Anything else? Yeah. Right? How much is that? 70 bucks. How much?
80%.
Right? Next, so that's the first part, calculating momentum. The second part is find the average force exerted on the tummy by the seatbelt during the crash if the duration is 0.1 second. How do we find force? F is equal to what? Mass by acceleration. Or I gave you a next formula yesterday. Saturday. Change in momentum over time. Very good. Change in momentum over time. Right? So we know the time. Right? We know the time. We know the time is 0.1. Right? What's the change in momentum of the dummy? Bob? Huh? Huh? 1820 to 0 because the QQ was at rest. So the change in momentum is 1820 to 0.
Why is it 0?
Huh?
Oh, you have to press after.
Yeah. Actually, the other way around. Yes, you are correct. I write it back. It should really be 0 minus 1820. Right? Because the final is 0 and the initial is 1820. So when you work it out, I got 18,200 Newton. Anybody get that? Right? Yeah, 18,200. Yeah, that's Newton. And the last part, what was the last part? What you all didn't know. The last part is this. Right, let's just pass it. With the removal of all protective features, the dummy was subjected to another crash test with the same initial speed. If the time, this time it was subjected to a lethal decelerating force of 4,500 calculated duration. So look at what they give us. They gave us the force, they said same initial speed, and they want us to find time. So we can go in reverse and work it out now. Duration of time, right? So we can go in reverse and work it out.
Oh, yeah.
Right? So we have force, we have same speed, we have to calculate duration. Any ideas? Right? So what you have to learn to do, right? And you might see this in physics, right? You might see a situation where you never really did a calculation like that. So what you have to learn to do is to list out everything you have. I have force, I have same initial speed. What would happen to the dummy after? What do you think his final speed will be? 0. What's the initial speed again? How much? Right. Did his mass change? Same dummy, right? So the mass was how much?
7.
7. And they want us to find time. So time is the problem. You have to figure out now, okay, how I can put all this together. And how can I put all of this together and find time? Think about it. Right, Nimble. Okay, all right, yeah. Try something else. Answers? Think about it. So tell me, formula use it. Sanjaya. Jaya. But that's good. Wait. Sanjaya is P-E-Y-E. Right? All that. Right. So what formula are you thinking about using? Which one combines all those letters there? F, M, U, and T. Let me just look back at part 2. The back at part 2. F is equal to right, changing momentum. Changing momentum over time. MV minus MU and that's okay? Right. I just have one question before we start to substitute, right? They say a decelerating force. So am I going to put 45,000 here? Minus, very good. Right? Very good. What's the final momentum? 0. Initial momentum is still what? 18 something or something?
Times. I mean, 20. 18 times.
18, 20 times. And then you have to make T the subject of the formula. So carry it up, divide it. So I have minus 1820 over minus 45,000. 0.04 seconds, 0.04 seconds. All right, nice. So that's the way you handle momentum. The next thing we have to look at, we just talk about it now. Things that you did in form 1 or 2 or 3. Remember energy? You must do energy in form 1 or something. Yes.
So we never did physics in form 1 or 2.
Integrated, you'll know with energy, kinetic energy and potential energy, right? Right, so it have 2 main types of energy, kinetic and potential. Have plenty other types, right? But the 2 most important types are kinetic and potential. Kinetic is what? Energy due to what? Motion, and potential is energy due to height, position. Okay? So we have 2 types of energy to look at, kinetic and potential. And then we have something called the conservation of energy. So we'll spend some time on all of those, right? Actually, let's just talk about it while I have both here. Right? So if you look here, this handout in the group as well, right? If you look here, we're going to take a look at energy. So I want to read out these 2 pages. So, right? So we have all these different types of energy. We have chemical energy, electrical energy, kinetic and mechanical, gravitational potential, elastic and potential, electromagnetic, nuclear, sound and thermal. All these are different forms of energy, right? And there is one conservation that we have to learn. The most. You pack up already. I'm going to give you a note. I'm going to give you a note just as well. Right? There is one law I want you to remember, and the law is energy can neither be created nor destroyed, but merely converted from one form to the next. So we have to be able to see this conservation in different elements. All right. So for example, let's look at an electric fan. Vinaya, since you're ready to go home. An electric fan. What are the energy conversions in an electric fan? Well, what's the source of energy?
The electricity.
Electrical energy. And that electrical energy doing what?
Making
So it's converting electrical into mechanical. And what type of energy you are receiving?
wind.
Wind and?
Kinetic. No.
Wind and? Let's just hear the wind. So let's hear some sound. And it always produce heat. Right? So your electrical energy that being supplied is converted into mechanical energy, and that mechanical gives you wind and sound, right? And heat. So there's always that conversion of energy. All right, so I want you to read off all types of energy, and we are going to focus on kinetic and potential next. Right? Power, energy, and kinetic and potential.
Right.
All right, so we can stop there.